1.3 one-sided limits. So the functions we have considered so far have been defined by simple formulas, but we're going to get into kind of piecewise limits. So we're talking about having graphs, like that's why we did piecewise in our pre-calc review. And we're going to talk about doing limits from different directions, so from the left and from the right. Okay, and it really sounds complicated, but actually, really it isn't, so just stay with me. So remember that a function is a rule. So for this particular function, the rule of the following: x squared only for less than or equal to 1. So we're only having an x squared graph at 1 and behind it. Okay, we're having a 3 minus x graph after 1. Okay, so we did these. We actually graphed these on our pre-calc packet. Okay, so for example, since 0 is less than or equal to 1, where would we check that? We would check that in the x squared function, because that's a less than 1 value. Okay, so the value of 0 is 0. So 0, 0 is a value on the x squared graph. That makes sense. 1, I'd test that still in here because this includes 1. 1 squared is 1, so that's where I'd get that value for this function. Okay, 2, now I'm bigger than 1, so I put it in here. 3 minus 2 is 1. Okay, so I have to switch where I plug it in. This tells me where my x's go. This says any x less than or equal to 1, I plug into the top one. Any x bigger than 1, I plug into the bottom one. Okay, so we investigate limiting the behavior now as it approaches 1. So this is where things get a little bit different. So if I'm looking at now that 1, that spot where we switch graphs, I want to see the limit going to 1. Well, look at the limit going to 1. As I get really, really close to 1, I'm getting really, really close to 1. I'm getting really, really close to 1 on the other side, because the other side's a different graph. This one's the x squared. This is a 3 minus x. So when I'm getting really close to 1 on the other side, I'm getting really close to 2. So that would be a point of discontinuity. They are coming into different spots. That's OK. You're going to see the picture in a second. They break. So it's just a point of discontinuity. We can prove that by the limits. OK? So when we're doing this right here, that minus means from the left, negative. That plus means from the right. So when doing one-sided limits, that negative sign, there might be something you want to write down in your notes there, is from the left is the negative symbol next to the number, and the plus sign is from the right. So if we were evaluating a limit of 1 for this graph, the from the right would come from the 3 minus x graph, and from the left would come from the x squared graph. Okay, so that notation, again, limit as x approaches 1 from the left was 1. That's the thing we just talked about. This table says it's approaching 1, right? As it's approaching 1 from the right, from here, it's 2. Okay? Any questions so far? Biggest thing is the notation, okay, from left and from right. Okay, so further insight into this type of function is gained from its graph. We observed that x less than or equal to 1 for f of x squared is also part of the graph of f equals 1. It's coincide with the graph of the parabola, which makes sense, 1, 1. If x is bigger than 1, then we plug in a 3 minus x, and that part of the graph is going to be linear at the slope of negative 1. Okay, so when we look at this picture here, here's the picture of that situation. So here's my x squared, stops at 1, jump up to here, and there's my 3 minus x. So you can see it doesn't have a continuous, it's discontinuous because at this point we jump and go a different direction. Okay, now if they were on top of each other, that'd be continuous. Okay, so for example, if this happened to be the same point, then it would be continuous and we'd be okay in terms of continuity. Okay, so in general, okay, that's good. Okay, the left-hand limit as x approaches a equals L. So the left side as it approaches just our limit. So our limit is 1. And on the right side, it approaches 2 at 1. Okay, approaches 2, approaches 1. Okay, if the function has different expressions to the left and right, which I've already stated, the theorem provides a convenient way that it does not exist. So if they are different values for what it approaches from left and right for this function, it will be, the limit doesn't exist. Okay, so that's what this says here. So if limit from a to the left does not equal from limit a to the right, then the limit itself does not exist. So right there, what we just did, it does not have a limit because they go to two different spots. Similarly, guys, from that spot, I'll let you write this down, but from that spot yesterday where we had the two graphs, the 1 over x, how it went in different directions, so it's not going to the same spot, therefore it didn't exist. The one we just did was not going to the same spot, so it didn't exist. We have two differences, so therefore it does not exist. Okay. Okay, so for this example here, when computing one-sided limits, we use the fact that properties of limits listed in section 1.2 also hold for one-sided limits, so we can still use our properties from earlier. This one here says find the limit as x approaches 0 from the right for root x. So what are the restrictions for root x? What are the restrictions? So then it doesn't even, like, the left side of this limit doesn't even exist. Do you see that? We can't come from the left of a root x. Okay? So this is actually the only way we can evaluate this one. So simply this one, we know where root x starts. Where does it start? If I can plug 0 in, it starts at 0. So the answer to this one is simply 0. Okay? Because that's what it's approaching. When you're coming from the right of a, okay, if you don't, like, look at the picture, guys, gals. Okay, that's what a root x looks like. So if I'm approaching 0 from the right, what's it approaching? 0. It comes down and hits 0. So that's your limit. This is a situation from last class. This is the easy one. I have no problem plugging 0 in, so that's okay. I can plug the 0 in. Square root of 0 is 0. No problem. Okay. All right. Let's look at 2. Show that limit absolute value of x equals 0. Okay, and so we're going to talk about this. We're going to look at the left side and the right side of it. This is why, because we know the absolute value of x is technically, remember this is back to Math 20 stuff. Probably going to get tired of me referencing that, I'm sorry. Okay, absolute value of x is also, remember we broke that up into negative x and positive x. It's negative x for x less than 0 and positive x for greater than or equal to 0. Remember, it doesn't matter where your equal sign is. But we know that from Math 20. Absolute values are a combination of the positive graph and the negative graph. So we need to take the limit of these two. So we need to take the limit of negative x from the left side. So the negative side, right? Because we're coming from the negative. And then we need to take the limit of 0 from the right side for positive x. Okay, that's because, remember, don't forget, this is a v. So coming from the right, this is my positive x. That's a positive in x. Okay, coming from the left, that's my negative x. Okay, so in this situation, just looking at your graph, what do they both approach as they get to 0? Yeah, they both approach 0. So they both get 0, therefore this limit does exist. Okay, so your answer is 0 for the whole question. Like the whole thing is 0, you can say. Okay, question? What's up? Are you sure? Yeah. I like questions. Okay. So from the left and the right, they meet at the same point, 0, 0, which creates the limit. It's kind of a simpler one.
So if one equals 1 and the other equals 2.
Does not exist. So you just put limit does not exist. Like that was our very first example, was a does not exist example. Okay, the Heaviside function. Okay, your electrical engineering. Okay, it's named after electrical engineer Oliver Heaviside, 1859-25. Okay, and can be used to describe the electric current that is switched on at time t equals 0. So that's the Heaviside function. So essentially what that means is if there's no time, there's no current, right? You don't have any current if you don't have the switch turned on. Makes sense, right? And then 1 if it's on. Okay, now you might think that's kind of tedious, but as like currents get higher, I mean, we'll build upon this. But the idea is this. If you think about this graph is simply going to look like this. It's going to be here, and then it's going to be here. Okay, so for the Heaviside function, though, if I do the limit from 0 from the left, what's that going to be? It's a constant, right? So if you're saying, what do I plug it in for? You remember, constants we can't change. From the left, it's 0. That's what it tells me. That answer is just 0. From the right, it's just 1. Visually, that's how this works. If I'm coming from the left, I'm here. I get to 0. That's why we got 0. If I'm coming from the right, I get to 1. These are different, therefore, D and E. The limit does not exist at 0. Why? Because we got 2 values. We had 2 different values. Okay, questions there? Okay, I'm going to pause the video. I'm going to explain stuff a little bit. I see a lot of thinking going on. I'm just going to explain it one more time. All right, so let's move on here. So example 4. So now we actually have a lot going on here. So we want to determine whether the limit of x to the negative 1 and limit x to 1 exists. So let's do negative 1 first. So let's look at negative 1 to the left, and let's look at negative 1 to the right. So I have to look at the graph there, and I have to see left of negative 1 would be which function of my 3? The top one, right? Negative x minus 2 is less than negative 1, so that's the left. Okay? Good? And to the right, which one would I use? This one, right? To the right, because this one's the section to the right of it, so I'd use x. So I'm going to plug it in. We put negative 1 in here. We have no restrictions. A negative 1 is a positive 1. Minus 2, I get negative 1 for this limit. If I plug in negative 1 for x, I get negative 1. They are equal, therefore it does exist. This one exists at negative 1. Okay, so first thing, left and right of the value they asked me to evaluate. Since I did the left, this was the left of it. This was the right. Therefore, these two are equal, so it does exist. Okay, question on that one? Yeah. Right, so it's immediate to the right because this is in pieces. So here's negative 1. The first step where I'm greater than negative 1 is right here, x greater than negative 1. So this piece, so they kind of go in order, right? So in terms of the number line, like if you think, and then we have 1. So this guy is this section. This guy is this section. And then this guy is this section. Does that make sense, Ryan? Yeah. And so this one is immediately coming from the left. Right, it's the one that's actually going to come to that point. And so having it in the inequality kind of gives that away. And so conversely, if we're doing the next one, when we do limit x goes to 1 from the left, it's going to be this guy. Because right there, that's the left of 1. X less than 1. Okay, I don't use all the way to the left because that's not that's not of the 0 we're looking at. It's not the closest. This is 2 pieces away. Okay, and then here, limit as x goes to 1 from the right, we'll use x squared minus 2x. So we plug those in. I get 1 here. Plug this one in. I get -1. D and E for that one. Questions? Okay, I think I have the picture so you can see the graph. Oh, I didn't. Dang it. Sorry. Okay, the picture, I'll just draw it really quickly. So the picture looks like this is y. We got 1, 1. It's an open dot. And then it's going to go so that was what the graph looked like, which looks continuous, right? It's continuous at -1, just no problem. Then it jumped. That's why they didn't match, and then it kept going. So that's what visually that kind of proves our point. Okay, we all right? All right. Okay, so another red box here. So discontinuities, we call from section 1.2 the definition of a continuous function. Remember, it's continuous if you can plug a in. That's what it's saying. You don't have to write it down again if you already know this, but if you can plug a in for x, it's continuous. If you can't, it's not. Okay? Implicitly, this requires 3 things if f is continuous at a. F of a is defined. Okay, so it has to be in the domain. The limit exists, and then we also can plug a in for x. All 3 of the things have to be true in order for it to be continuous. Okay, for example 5, I am going to pause it, and I want you guys to try it, and I'm going to see how you guys do. Okay, people are still writing. I'll give you a second here. Okay, this is more on discontinuity, which is it's kind of just going over it further. It's in your book. Probably need to put that page there. But go ahead and try this one here. So try example 5. Just do part A. We'll do part B together if you'd like, but go ahead and try part A. All right, so one thing that we have to kind of make sure when you see these, a lot of you are like, I don't know where to start. Well, to start, first thing, this is a whole function. This function has something changing or going on at 0. So that's where we're going to check out what's going on at 0. So 0 is what we're taking the limit of. Okay? Now, the ones before, we had 2 spots where they changed. That's why we did it at 2 spots. We did it 1 and -1. This one's just 0. Okay? Now, what I'm going to do is I'm going to do limit as x approaches 0 from the left, which would be this one, left of 0. Then I'm going to do limit as x approaches 0 from the right, and that's going to be this one. If you're asking, what does this do for you? Let me finish these, and I'll explain how that comes into play. So this right here is going to be, put the 0 in, I get 1, right? This, I get -1. So already at 0, we have a point of discontinuity, -1, okay? Because they're different. However, if they were the same, we still would have a problem. If it was 1, this says x equals 0, so 0 is also a value. The only way they would have been continuous throughout if all of these were zeros. Does that make sense? Because this point at 0 is locking you in. You have to be at 0 for the limit. It's saying I'm at 0. This one's at 1. This is at -1. We have problems all over the place. Does that make sense? The picture, you guys see it in your book, is essentially you have your parabola. Up by the other side, don't I? You have a parabola at 1 here. You have a point at 0 here. And then you have the parabola here. So they're all three at different spots. Okay, for part B, let's look at part B here. Okay, all right, part B. So now we're taking the limit at 2. 2 is where some change is going on. Okay, but the weird thing is that from left and right, like I have a graph and I have a point. So from left and right, what one am I going to evaluate? The first one. The first one is everywhere but 2. So graphically, think about that. Starts here, up 1 over 1. This is what the first one's saying. It's everything but 2. So this graph is going on both sides of 2. This is like this one. At 2, we get 1, which is just a point. So you already know it's not continuous. Okay? Because this is telling you a single spot. If it's saying equals, guys, that's a point. Now, if you're saying, well, 1's a horizontal line, Mr. Banker, it is, but only at 2, it's just a point of the line. Okay? So, why this helps us, because what happens is you're going to do the limit of this. You're going to do limit, x approaches 2 from the left, you use this one, and you do limit as x approaches 2 from the right, and you use this one. Using the same one, you're going to get the same answer. They're approaching, what is this approaching both ways? 3. 2 plus 1. It's all right. Okay, it's approaching 3. Oh, so it's continuous. Oh, let's go back. What's that say for we just wrote down the 3 rules. What's it say? It says f of a is defined, which it was. The limit f of x exists, which it does, but does limit f of x equal f of a? It doesn't, because this guy is at 2. Or at 1, excuse me, sorry, 2 is at 1. So it's separated. It's not continuous by that third rule.
So which one's f of a?
This guy here. There's no value here. The value's there. So that means that f of a, so if I said, Dana, what is f of 2? By that chart, what would you tell me? No, yeah, if I said what is f of 2, which means x is 2, what would you tell me the value is? No. At 2, it's 1. See what I'm saying? So it does not equal the 3. Therefore, it's discontinuous. We all right? Doing some hard thinking? All right, we got one more example. There's a picture of it too on the, or no, there's not a picture, but it explains it in the book too if you want to look at it. Okay, all right, let's do example 6 here. All right, cost of a long-distance nighttime phone call from Pine Bay to Hester is 26 cents for the first minute, 22 cents for each additional minute, or part of a minute. There's a minimum charge of 34 cents on all calls. Draw the graph, the cost in dollars of a phone call as a function of time. Where the discontinuous, is this a, oh, excuse me, where are the discontinuities of this function? So you're kind of drawing this guy. So we got to kind of understand what's going on. So first off, we know the minimum charge is 34 cents, no matter what happens, right? So that means like our first cost, our cost at essentially right away is 34 cents. But how does it change or how does it grow? And where, well, first off, how long is it 34 cents? When is the call more than 34 cents? What's that? After the first minute. Yeah, so it's 0t1. Whoops. It's 1. This is why. The rules say as soon as you hit, and it's going to be equal to 1, yep. And sorry, 0 doesn't count because 0 would be no phone call. Okay? So as soon as you hit 1, you're right at the 34 cents. This is what it's going to cost you. Even though it's 20, so it's 26 for the first minute, but that's only going to kick in if you're over 34 cents. Because 34 cents is the minimum you get charged. Okay? So that's what's going to happen here. As soon as we hit over 1 minute, if I go 1 minute and 1 second, okay, that's going to be automatically counted as how many minutes? 2 minutes, right? So 2 minutes would be 26 cents plus 22 cents, so now you're at 48 cents. Okay, so as soon as you get from 2, so it's going to be like this. So 26 plus 22 is between 1, not equal to, dang it, t and 2. Okay, and then it keeps growing like that from there. So then it goes 26 plus 2 times 22 for 2 less than equal to 3. Okay, and it keeps going like that, etc. Okay. So what they're asking us are where are the discontinuities? So this is a step function, they call it. So what happens is, let me see, I forgot if I put it on here or not. Nope. Okay, so what happens is 34 cents is your first price from 0 to 1. So if you're doing this graphically, times down here, so there's 1, 2. Okay, so if we do, we'll just kind of make it for easy for us here. We'll call this 34 cents right there. It's 34 cents right there, all the way up to a minute. Okay, and then at the next spot is going to be 48 cents. Okay, and that starts here and goes there. Okay, and then the next one is 70 cents. And it goes here. And the next one is 92 cents.
Why is there an open dot equation?
There, because at 0 time, they can't charge you.
Oh.
Okay, and then here. Okay, so it essentially keeps going like that every time. So it says where are the discontinuities? The discontinuities are where? Where are they? Start of each minute, correct. At start of each minute, we jump. We jump. So that's your point of discontinuities, is at every start of every minute. Okay, you can evaluate that, and I won't do this because it's a little tedious. You could do the limit of 2. If I do limit 2 from the left, what's it approaching? 48 cents. If I do limit of 2 from the right, what's it approaching? 70 cents. That's your definition of discontinuity again. Okay, using a step function. Okay, so one-sided limits. We are done with that.